Thank you very much, dear friends, dear colleagues. So, good afternoon, everybody. So, I would like to talk about the nucleus and how to excite it. And for this aim, I would like to use bound or almost bound electrons. And first of all, I would like to give some motivation why it is so interesting and why we should study this. If we go back to history, and look for the atoms, when we manage to excite ensembles of atoms and quantum mechanically control them, then we invent so-called lasers and like current status of technology unthinkable without this kind of facilities. And another example is atomic clocks. The accuracy of the atomic clocks nowadays reach 10 to the minus 18, and this is somehow amazing accuracy. So this clocks loses only several seconds for the whole age of the universe. And another even more fascinating technology is the quantum computers, which will be, I hope, discussed tomorrow, and therefore I will not speak too much about this. Okay, but if we now go to the nucleus, what kind of new things or new ideas can bring us if we manage to make a quantum control on them? So first of all, it's a nuclear laser, and since the nuclear excitation being less influenced by the electric or magnetic field, so the nuclear laser will be much more narrow, and therefore we can use it for many other applications. So another thing is the nuclear clock. Yes, so the nuclear clock can reach accuracy 10 to the minus 21, so which is even 3 orders of magnitude better than our best atomic clocks. And another, which I point here out, it's energy storage and release. If we find and we know that there are a lot of metastable electromagnetic levels in nucleus, we can pump them up with, if we know some another level which is not a metastable, we can control in a control manner, pump it to this excited state, and then it's released to this metastable, and the energy is stored. And then, in order to release this energy, we can develop a trigger mechanism, like a triggering, and we trigger metastable state to some excited states, and then the energy will release. And so this is like a nuclear battery, and one can store the energy on the metastable electromagnetic levels of the nucleus. Let me give a small overview about the application of the nuclear clocks. So far, our GPS technology is based on the atomic clocks, and its accuracy reached to 1 to 10 meters, which is somehow limited by the accuracy of the atomic clocks. If we develop the GPS technology on the nuclear clocks, accuracy will be even centimeter to millimeter range, which allow us to make autonomous driving, freights, and companions trackings. So another is 3D gravity sensors. So the present accuracy is plus minus 2 centimeter, which allows us already to measure the change in gravity potential up to 2 centimeter. And if we do this technology on the nuclear clock, then we can investigate the monitor volcanic magma, how it's inside the Earth move. And another is tectonic plate movements, etc. Another interesting thing is the search for physics beyond the standard model, since we can suggest that our fundamental constant can vary in time, and if we know the clocks the frequency depends on this fundamental constant, we can search for variation of such a fundamental constants. So why we would like to make the nuclear excitation by the electrons? since actually a lot of nuclear parameters was delivered us by the electrons or muons. For example, the proton radius is known from the hydrogen and from ionic hydrogen. So the instrument how we probe the nucleus is actually the electrons and the muons. Also, the magnetic moments and various moments or electric quadrupole moments of the nucleus is also known from muon or from electronic spectroscopy. And therefore, we can think that we can also use the electron to manipulate or to control the nucleus. For this, there are 3 mechanisms, or even 4, but I will mention today only 3 of them due to lack of time. So first one is the nuclear excitation by electron capture. So here we create a hole in the electron shell, and this hole is released or by the transition from the upper electron. And this, if the energy is exactly matching with the nuclear excitation energy, then we can see the transition by the electron with the simultaneous excitation of the nucleus. Another mechanism is the nuclear excitation by the electron capture, when the electron gets captured from the continuum, depicted here, to the bound state, and if again the energy is exactly matched to the nuclear excitation energy, then the nuclei get excited. And the third mechanism is the nuclear excitation by 2-photon transition. If we have the electron which make a 2-photon transition, so 1 photon is emitted and another photon is exactly matched with the nuclear excitation, and the nuclei get excited. So I will review all of these 3 mechanisms, and let us start with the nuclear excitation by the electron transition. How is actually performed? So we shined with the X-ray and ionized one of the electron in the core shells, and then the hole is created, and this hole is then de-excited, yes, by the upper electron, and the nucleus get excited, and later we see the spontaneous emission of the nucleus. What kind of experiments and what kind of theory was measured and proposed for this mechanism? So actually there are several experiments in neptunium, gold, and osmium. So, but actually there is a problem in the theoretical description of this mechanism, and I will explain you later why. So in red I just pointed out the most trustable values. Okay, so here we should consider such kind of Feynman diagram. So the double line corresponds to the bound electron, and the bold line corresponds to the nucleus. And the electron and nucleus exchange the photons, and the excitation from the electron goes to the excitation of the nucleus. So the S matrix of such a process can be written in such a way, where we have a psi, capital psi is the nuclear wave function, and small psi is the electron wave function. Then if you make a multiple decomposition of this interaction operator, then we can come to this formula. And this formula shows that the electron and nuclear variables are decoupled, and then this integral can be replaced by the nuclear electromagnetic transition strength. And this actually, so I write it only for one electron, but if you have a many electron, so this is wave function of a many electron system. And is this integral, if we have the many electron wave function, is rather difficult to calculate. And in order to improve our precision, we need to use rather high power computers in order to calculate this. And another difficulties is another difficulties in this X-ray source. So usually the X-ray source was not so good, and therefore the width of this X-ray was rather large, and therefore it is difficult to describe the process of the whole creation. And if, as Yaroslav on the first panel explained us, that there are a lot of synchrotrons of the next generation will be built it produces much better sources for the X-ray, and we can see this process much more clearly. Okay, and what is the problem is with all this with this process, that this energy should be exactly the same as the energy of the nucleus, and therefore it is rather difficult to find such a system. We can overcome this problem if we look in another mechanism, so-called nuclear excitation by electron capture, where we can vary the kinetic energy of the electron. And adjusting the kinetic energy, we can find the energy or kinetic energy of the electron which exactly suits for the nuclear excitation. And this process actually was never observed, and we, together with our Chinese colleagues, whom are working on the heavy ion research facility in Lanzhou, proposed a mechanism and proposed a scenario how to observe it. So we generate the calculations and predict that there is a possibility to observe it. For example, for gadolinium, we find the nuclear excitation, which is around 60 kilo electron volts, and 1s binding energy is 59 kilo electron volts. So we need only the electron around 1 kilo electron volts of kinetic energy in order to match these energies. And then if we plot the radiative recombination signal, then we see that on the radiative recombination signal we see the resonance peak, which exactly corresponds to the nuclear excitation. However, this was calculation for the exact electron energy, but if we include the distribution of the electron energy of the electron beam up to 1 MeV or 10 MeV or 10 MeV, this peak will be a bit smoothened. Okay, another mechanism is two-photon transition. So here, as you know, that the electron can undergo to the transition with the simultaneous emission of the two photons. So, and particular this kind of transitions scales with z, with the nuclear charge as z to the power of 6, and therefore one can expect that this kind of transition will be more dominant for heavy atoms or for heavy ions. And we find such a transition for helium-like ions, so it means that we have only two electrons left in the atom, so 1s, 2s, for example, with the total angular momentum 0, and then it decays to the ground state only with the emission of the two photons. And because the one photon emission is completely forbidden. Okay, and what is the pattern? What is the spectrum of such emission? And we see actually that these photons can distribute energy between each other rather arbitrarily. Yes, so the distribution of the energy looks like this, like a parabola. And we see that the most probable that they will share energy, but it's also possible that the energy will be different. Actually, this process is nicely observed in GSI, in Darmstadt, and therefore, together with our friends in Germany, we propose an experiment how to observe it for the nucleus. Yeah. So if we have a electron level in between. So if we have not a two-photon transition, just as it is, which is described by this curve, but if we have also like a level in between, then we have a cascade transition. So the photon the electron can first decay to this intermediate state and then to the ground state, and then we will have such kind of peaks, so one and another for the first and the second photon, and therefore this shape will be modified. So we will not have only this kind of shape, but also some peaks corresponding to this cascade. But however, if we have a nuclear level in between, the similar situation might happen. So the electron goes to the ground state with the emission of photon, and the second photon will excite the nucleus. So this is like will be a virtual photon which propagates the excitation to the nuclear degree of freedom. And then later the nuclei will decay with the emission of a photon. Okay, thank you. So we calculate such kind of cross-section and find that the rate of such kind of channel corresponding to the total rate is 10 to the minus 9. So it's rather predictable that the rate will be 10 to the minus 9 because it's for nuclear excitation by the electron transition. It's also similar order of magnitude. And also we propose how to detect this, so one can make a simultaneous measurement of such kind. So we have ion beam, and then we collide it with a gas gadget. We create the helium-like ion, and then the helium-like ion decay, and then we absorb the one photon, the second photon, and the ion. Also, everything in the time coincidence, and then moving this detector, we can detect the nuclear decay. Also, we propose this mechanism also for detection of the thorium level. The thorium level, the first metastable state of thorium, it's around 8.5 electron volts, and this is a nice candidate for the nuclear clocks and so for nuclear lasers, and therefore, like all community searching for this transition, and therefore we use our mechanism to search for this, propose for searching this transition as well. Okay, here we propose such kind of scheme where we excite the electron in some electron shell, and then it's decayed via 2 photon, and then excites the nucleus. And then, depending on what kind of energy for the nucleus we assume here, we propose to what kind of electron shell one has to excite the electron. Okay, and so here we propose the graph here. So with a different color, it is represented different levels to which one has to excite the electrons in order to search for the nuclear transition in this range. Okay, actually, I hope I'm in time, and that's all what I would like to tell you today. Thank you very much.
Thank you, Andrew.